Good afternoon, and welcome to a new video series. In this series, we'll be discussing the first assignment in our Process Dynamics and Controls course. In this video, we were given a conical tank, and we are told to derive expressions and simulate the height in the conical tank along a given amount of time. As you can see, as already gone ahead and shown what we're dealing with, we are given a conical tank that is 8 meters high, and then we're given values for the top, the bottom, and whatnot. As we have flow going in, of course, we're given that as 0.1 meters cubed per second, and then we also have Q out coming out, along with a small radius at the bottom of the tank of 0.1 meters squared, and then the radius at the bottom is 1 meter, and the top is 5 meters long. And what we can do from here is we have to derive expressions so that we can go ahead and put them into our ODE solver, into our Python collaboratory code to simulate this conical tank. So let's go ahead and get started. The first things first, we said we want to determine expression for the change in height. So before we do that, we're going to do a change in the fluid, or change in V. So very simple, change in V, respect to time, is simply the difference between the two flow rates, right? Qn minus Qout. Right, fairly simple. Then we'll be using this throughout our derivation today. So from here what we can do is we can do a per unit mass expression to correlate the kinetic energy and the potential energy in this situation. And to simplify this situation a little bit in this expression, we're going to ignore the kinetic energy here at the top. Just to simplify the problem a little bit, we're going to say that the change in height is so small that it's negligible and we can kind of just dismiss it. So what we can do is make the kinetic energy equals to the potential energy. Right? So what we're going to have is rho GH simply equal to rho V squared divided by 2, right? Now there's one other thing in this segment that I forgot to discuss is that viscosity, rho. We are going to say that is negligible as it's all going to be the same liquid coming through, so we can go ahead and get rid of this rho on both sides. Then we can go ahead and solve for V. So we get V is simply equal to the square root of 2GH, right? Then we can go ahead more and say that this is our V out. So then we can go ahead and calculate our Q out, right? How do we do that? We have the velocity coming out. We simply multiply it by the area of how much is coming out, which is 0.1 meters squared. So our Q out is V out multiplied by AH, which is 0.1 meters squared. Sweet, so from there we could even go ahead and plug that into our change in volume, or change in velocity expression. So we have Qn minus AH, or square root of 2GH. That is our new expression. However, like I said, we want to find an expression for the change in height, and of course the change in height is also comparable to time. So what we're going to do here, we say that we want the change in height with respect to time, right? What we can do is multiply that by the change in velocity with respect to height, because that is also dependent on height. And of course, if we multiply this out, cross multiply, we end up with dv dt, which is up here, right? Very simple. And then one thing is this dv dh, we can rewrite this term as that is a change. And that, as you can see, we can use AC, as AC is based on height. The more the height changes, the smaller AC is. The more it's at 8, the bigger AC is, right? So we can rewrite this as AC, I'm actually just going to do AC times dH dt, and of course equals to this Qn minus AH multiplied by the square root of 2GH. So what we can do here is simply expand this out a little bit, right? So that we get DH dt, bring this AC over to the right side. We're going to have Q in minus Q out, which we said is now AH times the square root of 2GH, and then we're going to divide that by AC, right? Run it from the left-hand side, bring it down. Perfect, so there is our first expression that we'll be using for our ODE solver later on in Python. Expression for a change in height. Okay, and then there's two more things that we need to figure out from here. Of course, we're doing an ODE solver, so we're going to need an initial guess for our H naught, right? So let's go ahead and figure that out. What is our H naught equal to? Well, our H naught, how we're going to figure that out is simply by finding when dV dt is simply equal to 0, right? So this is when Q in minus Q out over AC is equal to 0. So what we can do is make Q in equal to Q out and solve that way algebraically, right? So we have Q in naught equals Q out naught, right? Then this Q out obviously is equal to this expression, so I'm going to go add that in. AH times the square root of 2G, and I'm going to add H naught because we're obviously going to find initial guess for H naught. So from there, we can go ahead and rewrite this expression in terms of H naught. I forgot this also is square root. So bring this out so that we get H naught is equal to, so then we're going to have Q in naught divided by AH multiplied by 2G, and then this whole thing's going to be squared, so to simplify this 2G, square root of 2G just becomes 2G, this Q in naught becomes squared, as well as this AH. So this is our initial guess for H naught, and we will be using that, of course, for our ODE solver in Python. And there's one final thing that I want to discuss is the value of AC. So as we said, as the height goes down and up, AC value changes, and we want to find some kind of expression for that. So of course, this is a circle. We gotta find the area of that, which obviously is pi r squared. We don't know that. So it is based on the radius, and we're going to be using that for our expression. So if we go ahead and draw out a table, or a graph of our, we're going to have our radius on the left-hand side and our heights on the x-axis. I'm going to say this is when the height is at the bottom, h0, and then this is at the max, h top, which is 8 meters. And of course, when the height is at 0, the radius is 1 meter, or you can say r bottom, and then at the top, it's r top, obviously. And how this looks drawn out, these are the 2 points, right? When height is at the max, the radius is at the max. When the height is at the bottom, the radius is at the bottom, or the minimum. So this is straight line, very simple. So let's write an expression from this, very simple from algebra, pre-algebra. We know we write the line as y equals mx plus b. So our y here is going to be our r, because that's where we're trying to find our radius. And then our m is our slope, which obviously is rise over run. So our rise, we're going to have r top minus r bottom all over h top minus 0, right? Of course, we have to multiply it by the x value, which is h. So So depending on the height, we'll find our radius. And then plus b, which of course is RB, our bottom. So with that being said, this is all we had to do on here. So we can go ahead and grab these three expressions, go ahead and use them for our OD solver in Python, and simulate this conical tank. Hello, and welcome back to Collaboratory. So I've gone ahead and already put in our import statements that we'll be using throughout this code. So from here, of course, like always, let's go ahead and put our constants of what we know onto this equation. Of course, I have our whiteboard back here, so I'll be referencing that for our equations and whatnot. So of course, we know that gravity is equal to 9.81. Then we have our top and our bottom. Our top is equal to 5 meters. Our bottom is equal to 1 meter, right? And then we have AH, which is equal to 0.1 meter squared, right? And then we have H total, which is equal to 8 meters. And then what else do we have? We know Qn, 0 is also equal to 0.1. And then what else are we missing? 1, 2, 3, 4, 5, 6. I think 2. AH, Qn, our top, our bottom, H total. Oh, T end. We know during 5,000 seconds. And then there's another thing. Yeah, this was actually 0.01. So, and then we know that it will be increasing by 1.2, right? So yeah, those are all of our constants and given values. And then I'm also going to go ahead and put our initial guess for HO in there, or H naught. That is equal to, I'm just going to put the whole thing and then square it. So I'm going to do Qn naught divided by AH multiplied by the square root of 2 times G. Alright, so AH times the MP of square root, and that whole thing squared. Brackets in, make sure it's all good. So Qn divided by with that divided by this whole thing, and that whole thing is squared. Okay, should be good with our HO value. So from here, of course, we're going to find or use our ordinary differential equations to use our solve IVP to get an estimate of what this will look over these 5,000 seconds. So what we're going to need to do, of course, is put on dH dt, but before that I'm going to create an equation that helps us find AC, right? We need to know what the radius is, so let's go ahead and put that in equation. So I'm going to define an equation, call it AC, right? And then we have to put in what it's going to need. So if we look, it's going to need H, our bottom, and our top, as well as H total, right? Those 4 things. Go ahead, and then what we're going to have it do is put in the equation for R, and then with R we're going to go ahead and return the value for AC. So we do R is equal, we have R top minus R bottom, right? R top, or no capital, R top minus R bottom, and that whole thing is divided by H top, so H total h total minus 0, so let's do h total. And this whole thing is multiplied by the value of h, right? And then that whole thing, we're going to add the intercept, which is our bottom, right? Make sure this is all good. This whole thing multiplied by h, this whole thing plus our bottom. Okay, then of course, like we said, we want to return the value for AC, which is pi r squared, so np dot pi multiplied by r squared, right? Should be good. Now that we have our value for AC, we can go ahead and define the function for dh dt. So I'm going to just go ahead and call it dh dt. Then this is only taking in the values of the height and time, right? So I'm going to put h and t. And of course, this is where I'm going to put in the value for f, as we're going to have a 20% increase in the feed. So the new qn is going to be qn naught multiplied by f, right? And then I'm going to go ahead and put value for AC, right? So it knows right? That should multiply this by pi and r squared as well. And then once we get that, then we can return the value of dh dt, right? So then we're going to be returning qn minus ah multiplied by ah is going to be multiplied by the square root of 2 times g times h, right? So we have qn minus that whole thing, that's going to be divided by AC, right? Since that looks good. Actually simplify this down, let's just do this, right? Should be good for that. Alright, and then we want to return an array of this actually. So array, and then we're gonna have this, right? Brackets outside. So we have qn minus ah times, right, so 2gh square root of that times ah, qn minus that, and that divided by AC. Alright, that should be good. Sweet. Alright, so we got all the equations in. Now we should be good to go ahead and use them together to get an expression, or get an array for the values, and then plot that out, right? So I'm going to go ahead and just call this the result. And then of course we're going to recall solve IVP. Function, we're going to have dh dt, right? Let's take in h and t. T-span, we're going to 0 to t end, of course. Right? And then, I don't think we need to do that. Just do dh dt, I'm pretty sure. Alright, 0 to t end. And then we want the array of, I think I got it. Small AP. DHDT, there you go. Got rid of one too many, sorry. Delete this out, and then we want the gonna say the array of H naught. Right. And then method, we want it to be true. Alright, so that should be all good. Oh, maybe we do need this. DHDT H comma T. Does that work? No. H not different. Yeah, we definitely don't need this. HT. Maybe this. Underscore R. Underscore R. 2. Oh, what? Sorry. It should be dense output. Right, there we go. There we go. Okay, my bad. Sorry about that. Okay, so from here now we can go ahead and plot this out, right? So t-plot, or okay, sorry. So yeah, just click t-plot, and we're just gonna linearly space this out. In space, we're gonna go 0 to tn, right? And then say 100. Start off with 100 points, right? And then we're gonna do h, give values to h from this result thing. So result dot solution, and then we're gonna pull these values out, of course, so we can put it in there. So result dot solution. We're gonna put it to the t-plot, and then we want to pull out first one. All right. Now we can add scatter, right? So we'll say fig 1. Let's make subplots, and then fig 1. Sorry about that. We're gonna add scatter. Where we want the x value to be, we said x is going to be our height, okay, so h, and then our y value is going to be time. Or actually, let's do the other way, right? Sorry, it's going to be t. This is going to be what do you say? Y-axis. It should be just x and y, right? And also, sorry, this isn't t, and this is t-plot, what we just tried to figure out. Let's see. There, ooh, no. Okay, so it's definitely from HO, so let's see, given that. AH times. See if that works. Oh, get the whole thing multiplied by 2. There we go. That should be good. There we go. Okay. Let's run this through. Hopefully that's... There we go. That's what we're supposed to be looking for. Okay. Thank you. Sorry. Okay. I'm going to make this look a little bit better real quick.
with title conical tank height. Then we're going to have x-axis title. So it goes all the way up. Okay, I don't know why it's not working. It should be good, right? Whatever, let's see. X-axis we're making, that's time in seconds, sweet. And then y-axis, it'll make that height, in meters. Shift enter. Beautiful. Okay, that's what we're looking for. So here you go. This is what we're looking for. We're simulating the height, respected time. As you can see, it slowly gets better. Oh, no, sorry. Double click. I don't know how to zoom back out now. Okay, whatever. Wanted to show you if we increase this t end by an extra 10%. We see that it finally reaches its steady state a lot easier than if we had 5,000 instead of 50,000. But this is what we were looking at, up to 5,000. This is where it gets plateaus around there. Let's run back to 5,000 just for last time's sake. This is what it looked like. But we saw that as it reaches over 20,000 seconds, that it finally reaches that steady flow state. So this is the first assignment in this videos. Come back later and check out the second and third one. Thank you.